Imagine hearing distant sirens. Do you immediately assume it's an emergency near you? We often make quick judgments based on limited initial information. Is there a better way to evaluate new information and adjust our beliefs more accurately? Instead of reacting dramatically, we can respond more thoughtfully. Bayesian thinking is the process of updating our beliefs in light of new evidence. It's not about finding absolute truth, but about logically adjusting our confidence levels. Imagine you believe a coin is fair, giving heads a 30% chance based on prior knowledge. Think of it like a belief slider that moves based on new data. Here's your prior belief at 30% confidence. Now, new evidence arrives. You flip a coin 10 times and get 8 heads. This supporting evidence pushes your belief slider higher. Your updated belief is now 70%, reflecting the new evidence while considering your prior knowledge. This is the essence of Bayesian thinking. At the heart of Bayesian thinking lies Bayes' theorem, a mathematical formula that shows how we update our beliefs when we encounter new evidence. Think of it like revising your opinion after learning new facts. It quantifies how much your initial belief should change. The formula looks like this. P of A given B equals the probability of B given A times the prior probability of A, all divided by the probability of B. Let's break down each part. P of A given B represents our updated belief, the probability of hypothesis A being true given that we've observed evidence B. P of B given A is the likelihood, how probable the evidence B is, assuming our hypothesis A is actually true. This measures how well the evidence supports our belief. P of A is our prior probability, our initial belief about A before seeing any evidence. This represents our starting point. Finally, P of B in the denominator is the total probability of observing the evidence B, regardless of whether A is true or not. To see how this works in practice, let's plug in some numbers. Suppose we start with a prior belief of 10% that it's going to rain today. If we see dark clouds, evidence that's 80% likely if it will rain, and the overall chance of seeing dark clouds is 20%, then our updated belief becomes about 40%. Bayes' theorem gives us the mathematical tools to update our beliefs rationally as we encounter new information, forming the foundation of Bayesian thinking. Imagine you're a detective investigating a crime. You start with a prior belief about who the culprit might be, based on initial evidence. Then you get new evidence, a witness testimony. Using Bayes' theorem, you update your belief about the suspect's guilt. Your prior belief is just 1%, the initial probability that this person committed the crime. The bar represents this low probability. Now you get evidence. A witness says they saw the suspect at the scene. The likelihood of this testimony being accurate if the suspect is guilty is 90%. This is our likelihood bar. Bayes' theorem combines these. Posterior probability equals likelihood times prior, divided by the total probability of the evidence. Let's calculate 0.9 times 0.01 divided by the normalizing factor. The updated belief is about 8.3%, much higher than the initial 1%, but not 90% as intuition might suggest. The detective's suspicion grows, but remains cautious. This is Bayesian thinking in action, updating beliefs with new evidence. Imagine a patient visits the doctor and tests positive for a rare disease that affects only 1 in 10,000 people. The test is highly accurate, but should the patient worry? Bayesian thinking helps us understand that false positives can dramatically affect our conclusions. The prior probability of having this rare disease is very low at just 0.01%. This is our starting point before considering the test result. The patient gets a positive test result. The test is 99% accurate when the disease is present, but it has a 5% false positive rate among healthy people. To find the true probability of having the disease given a positive test, we use Bayes' theorem. This formula combines the prior probability with the test's accuracy and false positive rate. Let's calculate. The prior probability is 0.0001. The test sensitivity is 0.99, and the false positive rate is 0.05. The total probability of a positive test is the probability of true positives plus false positives. Working through the numbers, the numerator is 0.99 times 0.001, which equals 0.000099. The denominator is the probability of positive results from diseased people plus positive results from healthy people. The posterior probability is 0.00099 divided by 0.0505, which equals approximately 0.02 or 0.2%. This means even with a positive test, the patient has less than a 1 in 500 chance of actually having the disease. This counterintuitive result shows why Bayesian thinking is crucial in medicine. False positives from testing large populations of healthy people can overwhelm the true positives from rare diseases, making most positive results incorrect. In today's world of information overload, Bayesian thinking helps us evaluate news and combat misinformation. We all have prior beliefs shaped by our experiences and biases. When we encounter a news story, we should consider the source's credibility before updating our beliefs. Let's say your prior belief that a sensational claim is true is 50%. This represents your initial skepticism. Bayes' theorem mathematically describes how we update our beliefs based on new evidence. Here, the evidence is the source's credibility. Now let's see two scenarios: a reliable source versus an unreliable source. The reliable source has high credibility, leading to a significant belief update. The unreliable source has low credibility, resulting in minimal belief change. For the reliable source, our belief might update to 85%, reflecting the strong evidence from a trustworthy outlet. But for the unreliable source, even with the same claim, our belief only updates to 55%, because the evidence from an untrustworthy source is weak. This Bayesian approach helps us avoid jumping to conclusions based on sensational headlines from dubious sources. By considering source credibility, we make more informed judgments about what to believe. Imagine you're deciding whether to try a new restaurant. You've heard good reviews from friends, giving you a prior belief about its quality. Your prior belief is that there's a 60% chance the restaurant is good based on the reviews. As you approach, you see a long line of people waiting. This new evidence suggests the restaurant might be popular and good. To update your belief, you use Bayes' theorem. It combines your prior belief with the likelihood of seeing a line given that the restaurant is good. Applying the calculation, your confidence increases from 60% to 85% that the restaurant is good. However, the long wait time is a factor. You weigh the 85% confidence in quality against the inconvenience of waiting. Your final decision considers multiple probabilities, quality confidence versus time cost, making it a probabilistic choice rather than an absolute one. Bayesian thinking is fundamentally about adjusting your confidence levels based on new evidence. It's not about being right or wrong in absolute terms, but about updating your beliefs probabilistically as you encounter more information. This approach encourages you to think probabilistically and always consider the source and reliability of information before jumping to conclusions. Rather than forming opinions based on isolated facts, you continuously weigh evidence. Remember this reflective takeaway. Be a Bayesian. Question your assumptions, seek evidence, and update your beliefs accordingly. Just like a thinking brain that constantly processes new information, Bayesian thinking keeps your understanding flexible and evidence-based.